modular spaces of manifolds. So, can I'm going to check first, can people downstairs hear me? And if they do, do they have any way of telling me? Let's suppose that they can. So I want to explain. Okay. I'd like to explain something that I call modular spaces of manifolds, and I want to spend the first few minutes giving you various different models of what we might mean by that. There'll be different models might be familiar to different people, but we're all talking about the same thing. So the first thing I want to do is I will fix. Let W be a compact smooth manifold. And if it has boundary, which it's allowed to have, then I'm going to insist that it comes with a collar. So if the boundary is not empty, so let the collar C be given, and I'll write that as an embedding of a half-open interval across the boundary of W into the boundary of W. And sometimes we'll refer to the collar and sometimes we won't, but it's always implicitly there. And what I want to study, we want to study smooth fiber bundles with fiber W. And because I've got this condition on the boundary, I'm going to have one more piece of data. It's going to be a smooth fiber bundle with fiber W and trivialized boundaries. Okay, what does that mean? I.e., fiber bundles with structure group the group diff subscript boundary W, which is the following thing. It's the topological group of diffeomorphisms W. So it's a diffeomorphism, not a homomorphism. And the boundary in the collar play the following role, such that there exists an epsilon with right. So they're diffeomorphisms which are the identity on an epsilon collar. Okay, so the collar in principle is quite long. We just insist that they're the identity of some unspecified, it's not part of the data, it's just a condition. There's some small epsilon for which the whole thing is the identity. And I said in words that I haven't written that this is a topological group that should be given the Whitney infinity topology. If you're not so familiar with that, let me just say one word. That means if I have a sequence of diffeomorphisms, in order for them to converge, certainly point-wise they have to converge, but also the derivatives have to converge, and all the high derivatives have to converge point-wise as well. So there's a topology that have those properties. So there are several Homotopy equivalent models for a modular space of manifolds of shape W. I want to introduce three of them. The first is probably the one that's most familiar. I'll call that B-diff partial W. And it's just the observation that diff partial W is a topological group. So it has a simplicial nerve and a geometric realization of that, i.e. it has a classifying space in the simplicial sense. So we can form a standard semi. So I always prefer using semi-simplicial things, but you allow you to whatever you like, semi-simple normal. No, and hence classifying space. So that's one space. I can also so that was a topological group and it had a classifying space. I can also make a certain topological groupoid in the following way. So also have a topological groupoid, which I'll write as follows. I'll write it as if particle of W acting on W. So that's the groupoid whose objects are W, and there's a morphism from the morphisms are the diffeomorphisms. Take W somewhere. And everything has a topology. W has a topology because it's a manifold that means a space. The diffeomorph group has a topology, and so you can think of that as a topological group. So there's an equivariant map.
The chalk is a varying quality.
Can I interrupt for a second? There's a technical problem. The people downstairs cannot read. They can hear you. So imagine you're Feynman and you're recording the audiobook. Try to write as little as necessary and speak as much as possible. I know this is a challenge.
Okay. No, it's easy. Speaking more is easy. It was the other way around.
It's like grave secret when you talk, right?
Okay.
They can hear me very well, but they cannot read even if you write big. So.
I see. Okay, so
you can continue writing. Just make sure that you explain what you write.
yes,
Just like you.
so there's an equivariant map from W to a point. And the only map there is from W to a point is equivariant for the action of the diffeomorphism group. And if we take classifying spaces for the two groupoids, this gives a map from the geometric realization of the nerve of this groupoid, so the translation groupoid of the diffeomorphism group acting on W, to the nerve of the diffeomorphism group acting on a point, which is what I was calling the classifying space. Now, each fiber of this map is a copy of W. Would you agree? And if you're willing, yep.
Not to place more demands on you, but back here we can't see the lower part of the board.
Is that okay? What sort of height is okay? I forgot here.
Yeah, but
Okay.
fine. At least for me.
So the actual fibers of this map are all copies of W at a point set level. And if you're willing to have a little bit of faith, you will grant me that it's in fact a fiber. Okay? That may or may not strictly be true, depending on how you make the geometric realizations, but let's not worry about that sort of esoteric. So this is an example of fiber bundle with fiber W, and I claim it's the universal example. The universal such fiber. Okay, so that's one model. That's a simplification model for the classifying space of this particular group. And it's probably the most familiar of the ones that I'm talking about. Nice. Okay, the second one, and I must confess this is my preferred model. I will judge you if this is your preferred model. I'm going to write an M of W and it's the following topological space. So I'm going to choose, first of all, an embedding of the boundary of W. I'll call it E partial, and it's an embedding of the boundary of W into infinite dimensional Euclidean space. Okay, just choose one, and that's a safe thing to do because the space of such embeddings is contractible by Whitney's embedding theorem. And now I want to look at the space of embeddings of W into the sort of half Euclidean space. So the half open interval minus infinity 0 across O infinity, and this is just going to be the space of embeddings of embeddings of W into this half open Euclidean space, such that, and now the collar comes into play again. On the collar, they look standard. So for all small t. So on the collar, they're just given cylindrically. So if I can draw a picture of such a thing, this is my R infinity. The manifolds are always now to the left of R infinity. Okay, there's no sort of left-hand half space. I've given my embedding of the boundary of W, and then I take all those embeddings that are sort of cylindrical near the boundary, and then they're allowed to go off and do whatever they like. But you have to have this cylindrical part. Okay? And again, I don't exactly specify in the embedding how long the cylindrical part is. It just has to exist. So similarly, again, by Whitney's embedding theorem, this is also contractible. This is contractible by Whitney's embedding theorem. And then I can set, oh, and it also has an action of my group of diffeomorphisms. Because if I have one embedding and I pre-compose it with a diffeomorphism, I certainly get another embedding, and it certainly continues to have this property because both the embedding and the diffeomorphism are standard on something. So diff partial W acts by precomposition. And I'm going to set a fancy E of W to be the quotient space. So just a straight actual quotient space of the quotient problem. I'll also point out that not only is this, so we have a contractible space, the space of all embeddings, it has an action of the diffeomorphism group, and furthermore that action is free. Because if I have a diffeomorphism that fixes some embedding, it has to fix every point of W, i.e. it has to be the identity. Now that's not enough for something to be classified space. You can't just take any free G space and take a quotient, it has to have something a bit better, for example slices. And again, I'm going to assert that this does. So this is good enough to be a principal diff bundle. So the quotient map is a principal diff bundle. Okay. And now I'll point out that what we did, we took a contractible free diff W space, and we took the quotient. That's another model for the classifying space of the group diff W, and so this is homotopy equivalent to the simplest model we have. But I quite like this model because of the following: that this actual set can be interpreted in a quite nice geometric way. So the reason I like this is because there's a bijection between the set, oh sorry. W, that's M. That's one of these. And there's a bijection between this space and the following. The set of subsets of minus infinity, 0, cross infinity, such that various things happen. One is that X is a smooth submanifold. So you have to think about that a little bit, but if I give you a subset of Euclidean space, it either is a submanifold or it's not. I don't have to give you more data. It is or isn't. So that's one property. It also X contains minus epsilon 0 cross E partial boundary W to some epsilon. Because of how we built the embedding, so just as a set, it contains it. And finally, X is diffeomorphic, or I should say there exists a diffeomorphism between X and W, well, the boundary of W. Okay? Now we have to think about that. What do I mean relative to the boundary of W? Well, by this second part, X contains the boundary of W in a standard way. So it makes sense to ask for diffeomorphism that preserves that standard. So this is just a set of subsets that happen to be submanifolds, happen to be diffeomorphic to W, and have some boundary data as well. And if you think about it, it's exactly bijection with this quotient, and so there's a nice topology on this side. And this is the way I like to think about the space of the manifolds. Okay.
Can you just intuitively say what the topology looks like on the right hand side?
Right. So here are things that are continuous as paths in this space. I can take my manifold X and I can take, for example, a section of the normal bundle, and I can move the manifold X along that section. And the section, in order to preserve this property, the section ought to be 0 near the boundary on some epsilon neighborhood. And basically, that is a neighborhood basis for the topology. Those are normal deformations.
So, can I think of the topology in a more metric way by Hausdorff?
I'm not an expert on that, but my friend really does.
Yeah, you can because you have imposed that they have. Oh no, you can.
So no.
If the manifold is interconnected, yes.
If the manifold is simply connected, you can. There's an issue. You could have very many parallel copies of X, and that would be Grant Hausdorff quite close to X, but would not be diffeomorphic without this W. So you have to get rid of things like that.
You would have double copies.
Yeah. Okay. So now I want so far these have just been naked manifolds. But we often want to talk about manifolds that have, for example, orientation, or manifolds that have a spin structure, or things like that. And in fact, even if you don't want to talk about that, we're going to have to. There's intermediate statements in what I want to explain that you have to talk about tangential structure, even if the end result doesn't include them. So let me tell you something about that. Tangential structures. So if I have a point in the space that I've just hidden with this board, if I have such a subset that happens to be diffeomorphic to W, there's a canonical so-called Gauss map, which I think I call tau X. And it goes from X to the Grassmannian of D-planes in R infinity plus 1. And I suppose I ought to say D is the dimension W. Okay? And it's the following very canonical map. At a point, little x, in capital X, I have a tangent space. And the tangent space is a D-dimensional plane inside R infinity plus 1. So it just sends a point in X to the tangent space at that point. I suppose I have to translate it to the origins speaking, but I won't put that in the notation. And this is continuous. So then, if the boundary of W is empty, and I want to write M theta W. Sorry, my notes have skipped something. So now I want to fix set vibration theta from a space I call B to this infinite Gaussian. And of course, I'm thinking of the infinite Gaussian as a model that is classifying space, the d-dimensional basis. That's what I mean if I have the right DOD by accident. So I fix such a set vibration. Now I can do what I want to say. So, if the boundary of W is empty, I want to write M theta W to be the set of an X in M of W. So, submanifold of infinite dimensional thin space that happens to be different to X, comma, a lift of tau X along theta. Okay, so theta and tau X both land in the same space, the Gaussian, and I ask for lift of tau X along theta. i.e. theta composed L to be tau.
So can you say again what do you mean with R infinity plus 1?
I mean R infinity. Well,
It's really 1 plus infinity, right?
Oh, yeah, or 1 plus infinity. Actually, more. I suspect that's not your question, is it?
No.
I mean, so where was I? So over here, I want to talk about this being a subset of some Euclidean space. Okay. So I want to think of the first hydrogen being an R, and then I also have an R infinity. Of course, I agree that it's probably more for R infinity, but I want to remember this first coordinate separately.
So 1 plus infinity.
1 plus infinity. You're quite right.
So why do you make this definition only for empty boundary? What?
I'm about to give you the version for the fixed boundary. It's a little more complicated because I'm going to fix a boundary condition. In fact, I'll do that straight away. So if the boundary of W is non-empty, then I'm going to fix a lift L sub the boundary W of the Gauss map of the boundary of W. And now the boundary of W is, I had this embedding that I chose and never mentioned anymore, of the boundary of W into R infinity, so it too has a Gauss map. But I want to think of it in the following way. The boundary of W is of course one-dimensional lower. It's D minus one-dimensional, and I want to get a D plane. But I can do that in a canonical way by using this first coordinate direction. So thanks for mentioning that. So the first coordinate direction directs the tangent space at X of the boundary of W. That's a D-dimensional subspace. So I fix a lift of that, and then I let M theta W sort of relative to this boundary condition be the set of X in M W, comma, let me write it like this, a relative lift. So it's it lifts tau x, and it extends the given one to the bound. Okay. Right. So there's a map. And okay, I'm not going to tell you what the topology is. It doesn't mix the obvious topology in that and the obvious topology of the map. So the map that forgets all of this theta structure is pretty obviously a fibration, I would say. Even though obviously it is a fibration. And the fiber over x is completely obvious, it's exactly the split of these. Over x, given by the space, we'll write it again. So it's the space of relative lifts extending my given one. And the point is, so the point is, this is the inclusion of the boundary manifold, so it's a co-fibration. This is a fibration because I asked it to be. And so the space of such things you can analyze by pure homotopy. Okay? So that somehow the difference between these spaces is homotopy theoretic in nature, not smooth manifold theoretic. And so if we can understand something about either one of them, then by playing homotopy theory, we can do something about the other. Okay, so as a little aside, so I asserted at least that this M of W is a classifying space for fiber bundles to fiber W and trivialized boundary. What does this M theta W classify? So M theta W with a boundary condition classifies the following sort of data, which looks quite high octane, but is not so bad. On the one hand, we have a fiber bundle pi with fiber W. So this is fiber bundle with fiber W. We also have a trivialization of the boundary. So we have, well, I can express that as an embedding of the bundle of a trivial bundle of boundaries into E over B. That's the data of the trivialization of the boundary. And it also comes with the following data. There's a map to BOD that classifies the vertical tangent bundle. So those tangent vectors to E, which are projected 0 and B. This classifies vertical tangent bundle. So that's given, that's not part of the data. You have such a thing, and the extra data then is a choice of lift L of that. So basically this, on each fiber, this is just a Gauss map. It's just a way of gluing all the Gauss maps together into a bundle. So it's a continuous choice of lift for every fiber. And there's one more bit of data, namely the boundary condition. Which is that that's right about the actual commute, namely that on the boundary it must be given by this constant term. This is just a family of exactly what this classifies. It's not terribly deep.
But the lower B is not the same as the
Ah, no. The lower B is the base of the vibration. Yes.
it's a different.
Yes, E minus X. Or at least not be. I'll never go with again. Okay, so let's think of an example of some of this, some of these structures. I want to explain to you the sort of range of things that can happen, even with a relatively simple structure, which is that of an orientation. So let me take a double cover of BOD, written by the oriented first. And let me also suppose W is connected. If it's not, you can analyze one component of W at a time. So let's think about some things that happen. So if the boundary of W is non-empty, let's think about that. If I give you an orientation of the boundary of a manifold and ask about whether it extends into the manifold, it either extends, in which case it does uniquely, or it doesn't extend. And there's two ways it could not extend. It might not extend because the manifold is not orientable, and so it doesn't have an orientation. Or it also could extend for a more silly reason, which is, for example, I chose an orientation of the boundary of the cylinder that's just not compatible. Right? In any case, the space of theta structures is either then any orientation of the boundary of W extends at most uniquely. So it extends uniquely or not at all. And in fact, what happens is that the space of lifts, so the space of lifts is either contractible or empty. First thing that can happen. So here you see that it has a sort of at most one part component. If the boundary is empty, then there's no boundary condition at all. Then we're just asking about orientations on a manifold. And then you know, again, two things can happen. Either it's not orientable and there's no orientations, or it is orientable, in which case there are two. And the space of orientations is either empty or has two contractible components. Okay? So remember I said W was connected. If W were not connected, I'd have 2 to the number of part components. And there's one more thing I'd like to say about this case, which is that in the second case, so when there were 2 components, we get a forgetful map, so manifolds with a choice of orientation, backing down to manifolds with no choice of anything, and this has basically a double cover. The 5 are 2 contractible components. So here's my question to you: is that double cover trivial or not? Anybody? So this is a double cover. So that's the question of, if I take a point in M of W and pick an orientation of it, and then move it around some loop in the space of M of W, does it come back with the same orientation or with the opposite orientation? So that's the question of, is there a diffeomorphism of my manifold to reverse orientation? So basically, that's a connected covering space, if and only if there's an orientation reversing diffeomorphism. And if there's not, then it's a discount. So for example, if the manifold is something like CP2, then M theta W is not connected. It has 2 part components corresponding to the 2 orientations of CP2, and you can't get between those by diffeomorphism. Okay, so the reason I want to emphasize this is that M theta W is not the classifying space of a group. It can be disconnected. So let's finish this remark. So this is this double cover is non-trivial if and only if W admits an orientation reversing different.
So which way does the arrow go from B diff oriented? I mean, NW is B diff W.
Yes.
And I can.
So this will actually be just two copies of B diff oriented. Because if you preserve one orientation, you also preserve the other, of course. So it's just two copies of the same space, but it is nonetheless two copies of that space.
It's one case, and in the other case, it's just B diff.
In the other case, it's also B diff plus. It's a wrong copy of B diff plus. So the thing is, on CP2, B diff is equal to B diff plus because you can't not preserve the orientation. So somehow, if you want an index 2 subgroup, you have to. It's not really a subgroup; it's just a double cover, not connected. Okay, so now I would like to explain. Okay, so this is some definition of some space of manifolds that, for all you know, is just always contracted or something. It's not. So I'd like to explain the main sort of technical tool for analyzing these spaces, which is a certain map out of MW to something constructed out of X-Bodley and Homotopy theory, a certain infinite space. And it's a parameterized version of the conjugate Tom construction, which probably everybody is familiar with. Parameterized conjugate Tom construction. And I want to do this moderately carefully because otherwise everything else I'm going to say will seem very unconvincing. So, firstly, I want to define a new load of tangential structures that makes sense when my manifold is in a finite dimensional Euclidean space. So I want to do it the following way. HQ define, just going to pull back theta, which is defined over the Grassmann D-planes in R1 plus infinity, that contains as a subspace the Grassmann D-planes in R3. And I'll just pull this vibration back one, and I'll call that BQ, HQ. Okay, so this is just a new vibration, has the same type as theta, but it's defined over the Grassmann D-planes in R3.
What does this Q do with the special coordinate, or is it not relevant?
Uh,
The first one.
I guess it should include the first coordinate. Yeah. Yeah, that would be more obvious when I write the next thing. Yes. So that's the new tangential structure that makes sense. If I have a manifold that happens to be inside RQ, then its Gauss map just lands in this subspace without any choice. It just happens to land there, and I can ask for it to. And now I want to let M theta W boundary condition, and I want to put two declarations. One of them is a subscript Q, which is going to be my manifold going to be inside RQ, and another is a superscript fat, which I will explain in a second. So this is just a subspace. The space of manifolds I've defined, and it's going to be ones that have two special properties. So this is a subspace of those x, L, such that two things happen. One is what I just said. One is that x happens to be inside -infinity 0 cross r q minus 1. So it happens to only use the first q coordinates, including a special one. And the second property is that x is fat. What this means is that if you make a radius 1 tubular neighborhood around it, that stays indented. How do I like to say that? The normal exponential map from the normal bundle of X to R cubed is an embedding when restricted to the unit disk bundle. Okay. So if I just shoot off all vectors of length 1 over in the manifold, that just gives me an embedded thing. Okay. Now let me point out something if you're not so familiar with tricks of the trade in smooth topology. Every manifold is slightly fat. Namely, there's some radius that always stays embedded. Okay. And so if I've got if maybe radius epsilon stays embedded, then if I scale my manifold by 1 over epsilon, it's now fat. Okay. So so this fat thing, it won't change the homotopy type. Okay. Scaling will always just get me into the fat part of the size of the then I don't have to make a choice of epsilon and how fat it is. You can also do. There's one fiddly thing. So of course I've chosen silently an embedding of the boundary of W. If that itself is not fat, then there's nothing I can do, of course. So don't do that. Now, right. So if the boundary of W is empty, I'll do the empty boundary case and now I'll tell you how you have to fix the boundary case. And I want to define a map from this space of fat embeddings in RQ to the Q-fold loop space of the Tom space of the following thing. The Grassmannian of D-planes in RQ has, of course, a D-dimensional bundle over it, canonically, but it also has a Q minus D-dimensional bundle over it, namely all those vectors that are orthogonal to that plane. And like it, so I'm going to call that gamma, I don't know, D minus Q. That's its dimension. That's a bundle on the Grassmannian of D-planes in RQ. I'm going to pull that back on theta Q. That's a vector bundle on B in Q, sorry. And then I take its top space.
The dimension of gamma D minus Q is Q minus D.
Sorry, the subscript ought to be, as you said, Q minus D. Yes. The subscript is supposed to be the dimension. Yeah. Right, so let me give you the formula for what this map is. So I have to tell you, if I give you a map, a manifold X and a theta structure L on it, I have to produce a map from SQ to this Tom space. And what map do I send it to? The following, I first think of SQ as being the one-point magnification. One-point magnification vacuum. And I've got my fatly embedded submanifold X, so I know its radius 1 normal, its disk bundle is embedded. That's what it means to be fat. Okay? So I can collapse down everything outside of the tune of the disk bundle. I just collapse. And that lands me in the disk bundle of the normal bundle of X, with its boundary collapsed down. And its boundary is, of course, the sphere bundle of the normal bundle. Okay? This is just by collapsing the complement of the unit disk bundle. So far, I haven't used L. I I just use X and the property that it happened to be fatly embedded. But now, because, let me just say, rewrite it and then get this one to this thing over here. So this is just the Tom space of this bundle that I talked about before in the model of disk bundle or sphere bundle, the one-point classification model. And what does this map L do? Well, maybe I call it L star or something. It's induced by L, where L star is induced by the fact that if I, no, I shouldn't call it L star then, L step or something, is induced by the fact that if I pull back this bundle, that's just canonically the same as the normal bundle of X. Okay, let's think about that a little bit. So by construction, this L map pulls back the d-dimensional bundle to the tangent bundle. And hence it will pull back your orthogonal complement to the d-dimensional bundle to the orthogonal complement to the tangent bundle. And of course the normal bundle is the orthogonal complement. Okay. So there's something I'm silently doing here, which is that because everything is inside R infinity, or RQ, there's a Riemannian metric on everything. And I always mean orthogonal with respect to that. I mean it over here when I define this R Q minus D, and I mean it when I take normal bundle as well. Using the metric. Okay? And in total, I've got a map from the Q sphere to the Tom space of this particular bundle, and you convince yourself it's continuous in the X. Okay. So this fixing the finite Q was just a sort of crutch. We really want the infinite Q limit. So as Q tends to infinity, we get all these maps fit together as you go to Q, as you get a map to what I'll write as loops infinity mt theta. And what this means is the colimit as Q tends to infinity of exactly the things on the right hand side. Okay, that's the definition, but that's if you want to do with it. For people who are of a more stable homotopy theoretic nature, I'll just say that mt theta is the Tom spectrum of minus theta Q of gamma D. So I pull back sort of theta. I pull back gamma D along theta, so the d-dimensional bundle still makes sense, always. I pull it back and then I can formally invert it to get a virtual bundle and then take it from spectrum. Okay? If you unravel what's happening, that's it for the examples. So they all fit together to form a map like that. And I also have my inclusion of my fat manifolds, so I can write it down so that they can see. All manifolds, and as I've said, by this scaling trick, everything is uncommon fat, so that inclusion is uncommon. So I'm going to pretend that there's a map like this, but of course the actual map is invert the. And I'll call that alpha W. So this is what I mean by the parameterized contrarian Tom construction. And if you think about the case, so this used somehow a bundle of manifolds through this MPW, if you think about the case of a single manifold, just a single X, this is just exactly the usual contrarian Tom construction that it is. It's just a way of putting them all together into a bundle.
Is the inclusion of flat manifolds actually a homotopy equivalence, or just weak?
Yeah. If I ever say homotopy equivalence, I mean weak. I don't know if it actually is. I sort of don't care. And even if there was, it wouldn't be a formula that meant it would just be some ludicrous. Okay, so that was the case of a closed manifold without boundary. Hopefully I said that somewhat. Yes, that's when the boundary is empty. I just want to tell you there's slight modification to do with the boundary is not empty. So if the boundary of W is not empty, I'll go through this a little quicker. Let me just say that the boundary condition on the manifold that we chose and the boundary condition theta structure that we chose determine a point in what you might call reach infinity minus 1 nt theta, i.e. what you get by writing q minus 1 instead of q there. So this is so the Pontryagin tone map for the boundary gives a point in the sort of D loop of this space. And then I'll just assert for you, then can get a map, or I'll give it the same name, that goes from M theta W boundary condition that to not the loop space of this space, which is what we got up here, but the space of paths from the base point to this distinct. So when I've got a boundary somehow, I can always think of that as being a path from the, or a cobordism from the empty manifold to whatever this boundary is. And then you don't get a loop, you get a path in this space. Now can I write that in a principal way? It's sort of, I write loop, but I mean path from the empty manifold to the point that this determines. So for many purposes, this makes no difference because, of course, all path spaces on a loop space are not equivalent just by choosing a path back to the base point, using the practice in H space. But sometimes it's important to have the point set model that actually lands here and not in the one that
So just to get the normalization straight, this empty theta as a spectrum and the form class lives in
degree minus t.
degree minus.
Yeah. Which is exactly what this choice of loops gives up. The bundle is d minus q minus d dimensional, but I look at q times. So let's go down. Normal class is going there to degree minus d. Okay, so this is something that you can set up as I have done in regionality for any manifold, and any theta, you can make this map. The result I want to explain to you is the relative miracle that in the case of even dimensional manifolds, and for an intelligent choice of theta that depends on the manifold, this map, either of these, that one or there, is an incredibly good approximation. Namely, it wants to be a homology isomorphism. And if you let W become more and more complicated, then it does become a homology isomorphism. That's the result I want to explain to you. Before I can say that, I have to say some things about something that's specific to even dimensional manifolds. The manifolds of dimension 2n. So whenever I had D before, I now have 2n. So for such a manifold, if tau W, say, from W to BO to N is a Gauss map of W, I want to do a homotopy theoretic construction called the Moore-Posnikov end stage of this map, which is a factorization of the map through a space B. So let sort of L theta B be the Moore-Posnikov end stage of tau W. So if you're not familiar with that, I will just spend a minute saying what it is. So firstly, that should be a fibration, that should be a cofibration. But more importantly, the map L should be n connected. Okay, so this space B looks like the manifold W in low dimensions, and this n is deliberately half this D. It is actually the middle of the manifold. And dually, theta should be n co-connected. Which is maybe less familiar, so let me start this out. So n connected means it's iso on pi I for I strictly less than n, and epi on pi n. And that should do with all data points that they have cannot be connected. Okay, so it's surjective in degree n, and then isomorphism in all strictly lower degrees. N co-connected is the dual thing. It's an iso on pi I for I strictly bigger than n, and it's mono on pi n. Okay? So in low degrees, B looks like W. In high degrees, it looks like B over 2n. And in degree n, the group, what pi n is determined. You factor whatever this is on pi n in a unique way as Fp mono. And that tells you what the group is. Okay? And it's a standard exercise in sort of obstruction theory or cells or whatever to show that something always exists and it's always unique up to equivalence between W and B over 2n. Okay? You just build it by attaching cells to W to force these properties to hold. We'll do some examples later and we'll sort of see how you actually produce such a thing, work out what it is in terms of things that you have known as well. I just want to say this gives a canonical tangential structure associated. And this, if I ever say the standard or the canonical tangential structure, this is what I mean. If you've got a W, you can always produce a tangential structure that it sort of wants to have. So for this W, for this theta, sorry, I want to define a certain subspace theta, which is what I get just by noticing that the L that I get in this way is not just any lift of theta. It's also n connected. Right? In general, inside here, we have all possible lifts of theta. That was what was meant to be. But there's a subspace of those that also happen to be n connected. So the subspace of x, L such that L from x to b is n connected. Okay? And we know it's non-empty because this L is an example. And this particular feature has a very nice property that a typical feature won't have, which is the following theorem. The proof I was going to give, but maybe I'll refer to the sort of problem or exercise. So let H or theta be the fiber homotopy equivalences of the map theta. So it's the set of those F from B to B will be equivalent such that theta composed F is equal to theta. Okay, so it's the monoid, it's a group-like topological monoid, fiber homotopy equivalence theta. So if the boundary of W is empty, then this acts on M theta N W. How? Well, if I've got one lift which is N connected, and I compose it with an equivalence, it's still N connected, and it's still this is an equivalence over B. It just acts on this by XL matched to X, I guess, F compose L. Okay? That's because composing with an equivalence is strictly commutes with a map to B. So it again gives an actual lift, and of course it preserves the property of being N. That's not the theorem, that's a fact. The theorem is that, and if I take the Borel construction of a homotopy orbit for this action, I just get my N done. So this is a way of formalizing this thing that I asserted earlier, namely the difference between M of W and M theta W, I guess I didn't draw that at the end, is somehow purely homotopy theoretic. This gives you an actual way to go down. It's not just that the homotopy fiber is something that can be described homotopy theoretically, which is true but less useful. This gives you an actual way of descending from this M theta N to M of W. Okay?
Sorry, is this in general, or is this particular choice of?
So this particular theta, it's important that it's M co-connected. Yeah. And it's also important that I only look at the subspace of maps that are M connected here. This is just I was going to give the proof of this, it's not very deep. It's just it's the over BO2N version of the statement that the space of maps from an N connected space to an N co-connected space is contractible. It's just the relative version of that statement. It's nothing very deep. Okay. So yeah, you can ask me about that in the example session if you like. I'd like to jump to the main theorem. So this is showing work of myself and Tom Joseph. And it says, let W to N be simply connected. The dimension should be 6, and theta be its canonical structure. Then this map alpha theta W from, let's see, M theta N of W with its boundary condition to, I erased it, yeah, to what the target, so this is, you can allow you to have boundary still, and then the target has to be such transient, it has to be this path space from the base point, which somehow is represented by the empty manifold, to the boundary of W with its structure. Is an isomorphism on homology. Is an isomorphism on homology with some provisos. One is that only in a range of degrees, and two is that it may not hit all components over there. So it's only onto the components that it happens to hit. So let me try to express this. Is an isomorphism on homology onto the components of the hits. In degrees, so it's not a isomorphism in all degrees, there's a certain range of degrees on which it's an isomorphism, and it's degrees star less than g of w minus 3 over 2. Oh, maybe I can fit in a g of w. Where g of w is what I think is the genus of w. G of w is the maximum k such that k copies of Sn plus Sn is a connect summand of w. Okay, so if 2n equals 2, and we're doing oriented surfaces, then this is the genus in the usual sense, and this is my measure of complexity of the manifold. Okay, so it's better to have more Sn plus Sn connect summands, at least from the point of view of this theorem. Right, so this theorem computes in this range of degrees. So again, the more complicated in this genus sense the manifold is, the better the theorem is. It gives you an approximation that's purely homotopy theoretic to the homology of MFP. And later, either tomorrow, well, both of them will talk tomorrow, either next talk or the one after, I'll do some calculations to convince you how calculable this is. If you want to compute, for example, rational cohomology of this side, then it's a go. So I'd like to put this, in my last few minutes, I'd like to put this together with this theorem. Because, while this result is quite nice, I like it, I must admit that it's probably the case that you're not so interested in computing things about MFTs. You probably just care about naked fiber dynamics without all this extra choice of doing all this stuff. And that's somehow the point of this theorem. Sorry, the top theorem. Because it tells you how to go from the space of manifolds with theta structure to the space of manifolds with So the corollary which is either side legs in myself as well, it says that under the same conditions, if the boundary of W is empty too, there is a map from M of W to loops infinity and theta for well construction homotopy automorphisms of the project theta, having the same property. So it is an isomorphism of multi derivative domains. So range, and again, because I've stated a slightly juvenile version for you, it's only onto those components that it hits. There's a better statement that I'll explain tomorrow that tells you why I keep having to say onto the components that it hits. Okay, so let me explain some things about this. Why does this act on here, for example? Well, I've taken a Tom space of this bundle, this vector bundle, pulled back along the map theta. So any symmetry of that map just acts on the Tom spaces, just on a point in the point sense. Just because their osmosis is strictly commute theta, it just acts on the Tom space, and it acts on him, i.e. this Tom spectrum and hence an actual group space. Then this corollary then immediately follows from this theorem. All you have to do is work out a version of this map alpha that is equivariant for theta. Because then the right-hand side, I've got rid of the boundary, so that goes away. The right-hand side is just this, and the left-hand side, and the theorem up there, gives me this M of W. Okay? So the trick is just whether a careful model. I mean, to deduce this from this, you want a careful model for alpha that happens to be strictly equivariant for theta. There's also a version when you don't have, when the boundary is not empty, but it's more fiddly. I mean, you can easily work it out if you want to work out all the statements at least. So that finishes what I wanted to say today. Tomorrow I want to explain this business about components, because there's a better theorem you can write down where the pi 0, where this space is not connected, and this space is not connected, and the map is actually a homogeneous isomorphism, and on pi 0 that includes information. It's saying that pi 0 of that side is saying pi 0 of that side, and that's a non-trivial piece of information. In fact, it's a theorem that is correct about the stable classification of manifolds. So I want to explain that, and then some applications and thank you.
Thanks to Oscar, and I wanted to apologize for those who are still downstairs. Difficulties. I hope we can fix this until the afternoon. And let's allow some questions for Oscar.
Can you say a little more about why odd dimensions are so different from the even dimensions?
So here's one way you can use this backwards that comes back to your point. So I'll assert for you, you can pick a map, there's a manifold W, so when you make its associative theta structure, you just get the identity map from BO to N to BO to N. You can make a manifold that just looks like BO to N on the N scale. Let me just assert that for you. Okay? So that means here you can pick that manifold, and here you can take just empty SO to N, and you have all possible characteristic classes of two n-dimensional bundles. And if you do that, then the homotopy morphs into the identity map is just cross-contractor. So that's entirely all. And you discover that there's some manifold which approximates loops infinity empty SO2 n. And you can calculate all the cohomology values. Fine. You can make a statement make sense in odd dimension. You can pick an odd dimensional manifold that approximates BO2 n plus 1, and you can try to get map it to empty SO2 n plus 1. But it's a theorem of Johannes Ebert that that map is never an isomorphism. There's no manifold. There's certain classes on empty SO2 n plus 1. They're the classes that come from fiber integrating the His-Wood L classes. And on any bundle of odd dimensional manifolds, that's 0. But on the analog of the right-hand side, it's not. So that means, at the very least, this is not the correct statement in odd dimension. I don't know what the correct statement should be. That's somehow, I think, the main problem in this subject, is to work out what do you think you should try to do in odd dimensions. I'm going to say tomorrow a little bit about what this pi 0 thing that people alluded to. That, in this case, that gives correct stable classification of two n-dimensional manifolds. And it's a feature of that subject that there's no nice stable classification of odd dimensional manifolds along the lines of the P. But there's a trick you can do for even dimensional manifolds that just makes sense and is not true for odd dimensional. So somehow these are two features of the same. I don't know what the answer is. There's some difficulty. I don't even know what the statement should be, so I can't try to prove it and see where I get stuck. It does not. The analogous thing does not prove.
Can you explain a little bit the reason why the theorem comes better if the genus is higher?
So the theorem is actually two different theorems. One of them is I can take my space on the left, and I can take the direct limit over connect summing with Sn equals to Sn. Just by iterating connect summing. And then there's a theorem that says that induced map is just a homogeneous and there's no range of degrees or anything. Then there's a separate theorem that has nothing to do with this right-hand side. It just says if I study the diffusion group of a manifold, and I study what connects something with Sn plus Sn does to that, that satisfies the so-called homological stability theorem in terms of this genus. So it says that in a certain range of degrees, and that somehow is completely orthogonal to how you end up calculating what the stable homology is. Here I've sort of combined these two results. This is not what you prove directly. You prove these two things separately, and they involve completely separate results. Somehow, for us, the reason having Sn plus Sn connect summands helps is that there's a trick well known in sort of four-manifold theory, but it works in all even dimensions, for removing double points of self-intersections using disjoint Sn plus Sn. So if you put an embedded n manifold inside a 2n manifold, non-embedded, sorry, immersed, it will generically intersect itself, and there's a geometric trick. But if you can find disjointing Sn plus Sn, you can do that self-intersection. And so that explains why having an infinite supply of Sn plus Sn is a very useful thing to have, because you can solve arbitrarily many such problems. And then there's a separate thing why connect something a single Sn plus Sn happens to have this homology stability. It's a bit difficult to explain why that should be. Well, first we have to understand why. It's a general phenomenon that holds for many groups of automorphisms. Symmetric groups, general linear groups over almost all rings that you can think of. Wave groups, mapping class groups, diffeomorphism groups. All these sort of groups of symmetry to things tend to have this stability phenomenon. And we know how to prove it, but I think I would understand why it's true. Yeah, I'd say that's mysterious. Yeah.
So I imagine you're going to talk about this tomorrow, but just so I have something between the two, I don't understand why I'm interested in the homology of
So you would be more interested, I claim, in the cohomology of MW, because the cohomology of MW is tautologically the ring of characteristic classes of bipolar with bipolar. And so, yeah, I'd say homology, but of course, really the way I want to use it is it's also cohomology. And the point is, when you compute, as I asserted you could, the right-hand side, it naturally is expressed in terms of characteristic classes. There are things that you get by private integrating certain polynomials in classes. So in the end, what it's doing is telling you these are all the characteristic classes of such.
Maybe the question is whether you can compute the homology.
Right. Of what? Using
Selections like
somehow, so my philosophy is that homotopy groups of modular spaces are just not, it's not the right question. Why do you especially interested in classifying families over a sphere? Why is it some kind of sphere? Cohomology classes of a modular space are universal meaning. It's a ring of characteristic classes of bipoles. I think homotopy groups here, you can ask that question, but I don't think it's the right question. I mean, most classified spaces are, of course, hit by ones. I1 has all the information, and the high stuff has nothing. And if you compute the homotopy group to doing something completely tautological.
So if they're not,
You know what components are actually?
Yeah, so I'm going to talk about that tomorrow. Yeah, there's a factorization of what you get.
just come back tomorrow and forget.